All right, welcome to Notes 4.127. We are talking triangles today. So let's start with the triangle sum theorem. I'm sure you're probably already aware of this, but the triangle sum theorem states that the sum of the measures of the interior angles of a triangle is 180 degrees. So the measure of angle A plus the measure of angle B plus the measure of angle C in our triangle over here is 180 degrees. All right, so let's talk about how we classify triangles. We can classify triangles either by their sides or by their angles or both. So when we're talking about the sides of the triangles, we've got scaling triangles, which have no congruent sides. And then we have isosceles triangles, which have at least 2 congruent sides, and equilateral triangles, which have all 3 sides congruent. And then when we talk about the angles, an acute triangle means that there are 3 acute angles. A right triangle has 1 right angle. An obtuse triangle has 1 obtuse angle. And an equiangular triangle has 3 congruent angles. Now let's talk briefly about the right triangle and the obtuse triangle. Is it possible for them to have more than 1 right angle? More than 1 obtuse angle? I'd like you to ponder that, and we will probably talk about it later. Okay, so on the previous slide I mentioned that we sometimes classify triangles by both their sides and their angles, and here's an example of that. We're talking about isosceles acute and isosceles obtuse, and then isosceles right triangle. And I would like you to draw me an example of each of these 3 kinds of triangles, and then come back and check your answers. The same thing with these down here, the scaling acute, scaling obtuse, and scaling right. Please draw me an example of each of those and come back and check your answers. So go do that, hit pause now. All right, so here are some examples of each. Yours might look a little bit different from that. One of the things I want you to notice is that I have marked congruency for my isosceles triangle to show that I have 2 congruent sides. It's not enough for them to look congruent, you must mark it. And I've also marked my right angles on my triangles. And just to be on the safe side, I've marked the obtuse angle in both my isosceles obtuse and my scaling obtuse triangles. All right, let's talk about the exterior angles of triangles. We earlier said that the sum of the interior angles was 180 degrees, but triangles also have exterior angles. And exterior angles are the angles that form linear pairs with the interior angles. So if you look at the example down here to the right, I've got triangle ABC. Angle 1 would be an exterior angle because it forms a linear pair with angle C. All right, and then we have a corollary to a theorem. Corollary to a theorem is a statement that can be proved easily using the theorem. And we're going to come into contact with our first corollary today. All right, let's talk about the exterior angle theorem. The exterior angle theorem states that the measure of an exterior angle of a triangle is equal to the sum of the measures of the 2 non-adjacent interior angles. So in our diagram over here to the right, we've got the measure of angle 1, the exterior angle, is equal to the measure of angle A plus the measure of angle B, because those are my 2 non-adjacent interior angles. All right, so let's see how that exterior angle theorem works. We've got this diagram to the right, and we need to find the measure of angle DCB, which is the exterior angle. And I know that the measure of my exterior angle, 3x minus 9, is equal to the sum of the measures of the 2 non-adjacent interior angles. So angle A and angle B, so x plus 73. And then we simply solve. So 2x equals 82, which means that x equals 41. But as in most math problems, at least the ones we face here in geometry, x is not our answer. We have to find the measure of the angle. So we have to go and plug that back in. So I take 3 times 41 minus 9, and I get, what is that, 114. So the measure of angle DCB is 114 degrees. So here's that corollary I promised you, the corollary to the triangle sum theorem. Remember, the triangle sum theorem states that all of the interior angles in a triangle add up to 180. Well, the corollary states that the acute angles of a right triangle are complementary. So the measure of angle A plus the measure of angle B equals 90 degrees. All right, here's an example that uses that. We've got a wheelchair ramp here. We've got a right angle. And the measure of one acute angle in the triangle is 8 times the measure of the other. So if this one is x, then this one is 8x. And we can use the corollary of the triangle sum theorem to say that 8x plus x must equal 90 degrees, which means that 9x equals 90, so x equals 10. So my answer is 10 degrees and 80 degrees, because those are the measures of the two angles. And we're going to do some vocabulary right now. So let's talk about congruent figures. Congruent figures are figures in which all parts of one figure are congruent to the corresponding parts of the other figure. And by corresponding parts, I am talking about, in polygons, we're talking about the line segments that form the sides and the angles of the figure. So all the line segments are congruent to the corresponding line segments, and all the angles are congruent to their corresponding angle. All right, we are about to write a whole bunch of congruence statements. And it is important that you understand what I am talking about when I say congruence statement. All it means is I am saying that one triangle is congruent to another triangle. Every single time we prove triangle congruency, we are going to write a congruence statement. Students seem to be a little confused about this in the past, but you will see me write a congruence statement every single time, and you need to do that as well. All right, so first we're going to look at these two triangles, and we are going to identify the congruent corresponding parts. So let's go ahead and identify the angles first. Well, A is our right angle, so angle A is going to be congruent to the right angle in the other triangle, which is angle F. And then my triangle, or the next angle, angle B, because it has a single arc, is going to be congruent to the other angle with the single arc, which is going to be angle G, which means that the remaining angle, angle C, must be congruent to the remaining angle in the other triangle, which is angle H. Now, ABC, FGH, those happen to be in alphabetical order, but it does not always work out that way, so do not assume that. All right, so in order for my triangles to be congruent, though, all their parts need to be congruent, so now I need to talk about the sides. So now I'm going to say that side AB, and I'm talking about a line segment, so I've marked it as a line segment, is congruent to FG. And it's very important that I write it in this order, because if A is congruent to F and A comes first, then F must come first. If B is congruent to G and B comes second, then G must come second. The order is critical when we are talking about congruence statements. All right, so now we've got BC is congruent to GH. And then finally, we've got CA is congruent to HF, and it must be written in that order. So now I can actually write the congruent statement. I can write that triangle ABC is congruent to triangle FGH. If I wrote GFH or if I wrote HGF, it would be wrong. The order is essential. I'm going to go ahead and highlight that because it's so important. The letter order is essential. Do not mess up the letter order. All right, and actually I wasn't paying attention. So these statements should have gone down here, right? We all know that A corresponds to F and so on and so forth. I just happened to write it up here because I wasn't really paying attention. Sorry about that. Okay, but it's not only triangles that are congruent, any polygons can be congruent. And the nice thing is, if they give us a congruent statement like this, then we know, because of the order in which they're written, we know what parts are congruent to each other. We know that angle F is congruent to angle S because they are both written first in the order. And we know that angle G is congruent to angle T because they come second, so G and T, and so on and so forth. So likewise, we know that side FG is congruent to side ST, right? That's the beauty of a congruence statement. It tells you which parts are corresponding. So this asks us to find the value of x and the measure of angle g. Well, we already know what the measure of angle g is going to be because it is congruent to t, and t equals 103 degrees. So we know that the measure of angle g is also going to be 103 degrees. So now we just need to find x. So I'm going to set 2x minus 7 equal to 103, and then I'm going to solve. So 2x equals 110, which means that x must equal 55. Right? Order is important. So now we come to our next theorem. It's the third angles theorem, and it simply states if two angles of one triangle are congruent to two angles of another triangle, then the third angles are also congruent. I would like you to pause this video and write a proof of that. Give it your best shot. Let's see what you come up with. Pause it now and then come back and check. So did you get an answer, or did you just give up? Well, I tell you what, I will give you the left-hand side of the proof. You have to give me the right-hand side of the proof, although I've been super generous and I've given you the given. I am going to ask you what items 2 through 8 are in the notes check for this unit. So see if you can come up with some answers. See if you can figure out how I did this proof. This section of the notes is all about isosceles triangles and how special they are. All right, so we're going to sketch a picture of an isosceles triangle. You don't have this, so go ahead and draw a quick isosceles triangle. The thing that makes it isosceles is that it has two congruent legs. So we'll go ahead and draw that in, and we might as well label our triangle. I think I'll call it ABC because I'm so original like that. Okay, so let's talk about the vocabulary of an isosceles triangle. The legs are the two congruent sides. So in this case, we are talking about AB and BC. Notice how I draw the segment marking over the top because I'm talking about the sides themselves and not their lengths. All right, my vertex angle is the angle formed by the legs. So that would be angle B in our example over here to the right. The base is the non-congruent side. So we are talking about AC in this case. And the base angles are formed by a leg and the base. And so we are talking about angle A and angle C. There's some theorems associated with isosceles triangles. And the first one states if two sides of a triangle are congruent, then the angles opposite them are congruent. So in my diagram over here, if AB is congruent to AC, then angle B is congruent to angle C. And the converse of that flip-flops that if and then. And so it states if two angles of a triangle are congruent, then the sides opposite them are congruent. So if angle B is congruent to angle C, then AB is congruent to AC. Students get confused between the two of these. They have trouble remembering which one's the isosceles triangle theorem and which one is the converse. So I do not want you to, when you use this in a proof, and you will, I don't want you to write isosceles triangle theorem. I want you to write if two sides congruent, then opposite angles are congruent. All right, and the reverse of that for the converse. I want to know that you know what you're talking about, as opposed to that you're guessing that the thing that you're talking about is the isosceles triangle theorem. Okay, so you're going to write it out. All right, so here's my example. I've got two congruent sides, so I need to name the two congruent angles. What are they? If you said F and G, then you are absolutely correct. So angle F is congruent to angle G. Is that the theorem or is that the converse? It's the theorem, but it doesn't matter because you are going to write it out. If the two sides of my angle or triangle are congruent, then the angles opposite them are congruent. You are going to write it out. All right, and then we have a corollary to the isosceles triangle theorem, and now we're going to be talking about equilateral triangles, which state that if a triangle is equilateral, then it is equiangular. Why is that a corollary to the isosceles triangle theorem? I want you to think about that and answer that question in the notes check. All right, and the corollary to the converse states if a triangle is equiangular, then it is equilateral. All right, let's do some examples. So we need to find the values of x and y in the diagram, and I'm thinking this right here is x. So what I have going on here is I have two different triangles, and I've got this big triangle, and it happens to be equiangular. Ooh, I didn't highlight very well. And then I have this smaller triangle, which happens to be isosceles. So if that's the case, then in my blue triangle, those two legs are congruent, which means that x equals 2y, but that doesn't help me solve for either one of those. And then in my big triangle, if it's equiangular, then it's also equilateral. So all three sides are congruent, which means that x equals 8, and that means that 2y equals 8, so y equals 4. All right, I've got a quilt pattern going on here, and we need to explain why ADC is equilateral. Well, I've got a number of ways of doing this, but let's talk this way. I've got a triangle in which these two angles are congruent. So if those two angles are congruent, then the sides opposite them must be congruent. So this side is opposite A, and this side is opposite D. Well, now all three sides are congruent, which is why it becomes equilateral. So if angles are congruent, then sides opposite are congruent. Therefore, have I ever shown you that symbol before, the three little dots in the form of a triangle? That is shorthand for therefore. Therefore, all sides are congruent, which makes it equilateral. Okay, now here's the million-dollar question. How do I know that triangle CBA is congruent to triangle ADC? Suggestions? Well, for this triangle up here, well, let's talk about this one down here because this is the easiest one. I've got all three sides are congruent, which means all three angles must be congruent. Okay, and then for this triangle up here, I've got these two sides are congruent, which means that the angles opposite them must be congruent. So angle C over here and angle B must be congruent. So what tells me that this last angle over here is congruent? Suggestions? I'm going to have you answer that in the notes check. And that brings us to the end of our notes. So please make sure to do the notes check, and if you have any questions, be sure to ask in class. Thanks.